Hey, hello, and a happy 5-day weekend. We're going to finish up 5.1, and I hope that you are following along with your guided notes. All right. So I said that factoring never ever goes away, and that's true. So let's look at how we would have factored this before. Something I'm going to look for first is I'm going to look for our greatest common denominator, or our GCD. That's the largest thing that is in each of my terms. It has to be in all three terms. I see that all three terms have a 2, and although two of them have more multiples of 2, I have to meet the needs of the lowest term. I also see that all of them have an x squared, and that is all I have for my greatest common denominator. Some of the terms have more things in common, but for all three of them, that's all that I have. So I'm going to factor out that 2x squared, and I'm going to divide that from each of the terms. So for the first term, I'm left with 3x. For the second term, I'm left with 2y squared. And for the last term, I'm left with minus y. All right, so this is what we would have done before when we were doing just regular algebra, but now we're going to go and move on to what would happen if we added this with trig. So it's the same idea. We're still looking for that greatest common denominator. Or greatest common factor. What is in each of our pieces? I see that in my first term, I have sine cubed x, and in my second term, I have sine x times cosine of x. Both of these terms have a sine x, and that's all they have in common. So I'm going to do what I did before, and I'm going to write what that greatest common factor is outside, divide it from each of the terms, and I'm left with sine squared x plus cosine of x. All right, this should be seeming pretty familiar, like what we've done before, just now we have more letters. Let's look at another example. So, cosine cubed x plus cosine x times sine squared x. I'm going to look for what that greatest common factor is. I see that both of the terms have a cosine x, and that's all that they share. So I'm going to write that shared term out front, and I'm going to divide it out from the other terms. So then I'm left with cosine of x times the parentheses cosine squared x plus sine squared x. Nice. Okay. So this is what we do when we're simplifying, when we're factoring. Now I could take a few of these solutions and I could keep going with them, but right now we're just focusing on that step of factoring. All right. Another idea that we use in simplifying identities is this idea of expanding. When we factor, we're taking a long expression and we're dividing it out to have different sets of factors that are multiplying. When we expand it, we are multiplying those factors out. So this is the closest example that I could think of that relates to our algebra days. So if I'm going to multiply that top term out, we call it foiling. It's really just distributing each piece to make sure that every piece is being multiplied. So I'm going to get, 16, if I do that outside, 4x minus 4x minus x squared. What do I notice? Plus 4x minus 4x. Those are going to add out to 0. So I'm left with, in the numerator, 16 minus x squared, and it's still over x. Is there anything that we notice that's happening when I expanded that, when I multiplied everything out? I hope we do. It's something called the difference of squares. When I have two terms that are being multiplied, and the first term in both of these factors are the same, and the last term are the same, but they have two different signs, one of them being a minus, one of them being a plus. It's a difference of squares. What it'll lead to us every single time is the first term being squared, in this case 4 squared is 16, minus the last term being squared, in this case x squared. It's a really cool pattern. If it helps you out to distribute each time or FOIL, that's a-okay, but this is a nice little shortcut. So another thing that I'd like to point out is, can I divide my function by that x? Can I divide that x squared by an x? Give me a second to think. The answer is no, and I really, really hope you said no. Because I know that if I'm trying to divide something in the denominator, it has to be in each and every piece in the numerator. I can divide an x into an x squared, but there's no x for me to divide into 16. So I have to keep it as it is. And that's 16 minus x squared over x. This is simplified. This is good. All right. So this is a good example of something that we could have done in algebra, the closest example I could find to what we're going to be doing in trig. So let's take a look at it. I have a nice long identity of cosecant of x minus 1 times the cosecant of x plus 1 all over cosine squared. That's pretty ugly, so let's clean it up. My first step is that I'm going to try and expand my parentheses, the things that's being multiplied. I notice here that I have that case where it's a difference of squares. So I look and I see, okay, I have the same first term, the same last term, and they're separated by two opposite signs, plus and minus. So what that means for me is that I can say it's the square of the first minus the square of the second. In this case, cosecant squared x minus 1. And the denominator is going to stay the same. So before, in the trig example, I said, we're done. But I think that we can keep going. Every time that I see a trig function squared, that should be a little alarm bell going off my head that maybe I can use a Pythagorean identity, especially if it's being added or subtracted with 1. That won't always be the case, but it's always good to check. So I go back and I remember, what is my identity that could help me out here? I have a Pythagorean identity that's cotangent squared x plus 1 equals cosecant squared x. And that's pretty close to what I need. It has a cosecant squared x, but I need a cosecant squared minus 1. And I think I can pretty easily do that, right? If I subtract 1 from both sides, making sure to keep everything nice and equal, and I have cosecant squared x minus 1 equals cotangent squared x. And if I have this part, which conveniently is equal to cosecant squared x minus 1, it equals cosecant squared x minus 1, that's telling me that I can substitute this long statement that we circled into just plain old cotangent squared x over cosine squared x. And I could pause here, but let's try and keep going, because I feel like we can get it down a little bit farther, especially if I have a cotangent squared over a cosine, we can do more. Let's remember, what is cotangent? Cotangent is cosine over sine, and in this case, that's going to be our numerator all over cosine squared x. In class, I talked about how we need to go over our fraction rules as well as our factoring rules, and I'm hoping that you can see why, because we got to keep going. If we remember, when we're dividing a fraction within a fraction, the numerator stays the same. That cosine squared over sine x squared stays the exact same. But the denominator, that cosine squared x, I'm going to take the reciprocal of it, so 1 over cosine squared x, and instead of dividing, now we're multiplying. Because isn't dividing the same as multiplying by a reciprocal. Dividing by 1/2 is this, dividing by 2 is the same as multiplying by 1/2, right? And I see something very nice, that I have a cosine squared x in the numerator and in the denominator. If I have something being divided by itself, divides out to 1. So I'm left with a 1 over sine squared x. And if we remember our reciprocal identities, I would know that this is really cosecant squared x. And that's our answer. So a lot of this chapter is simplifying identities and playing around with it like I did. I think it's pretty amazing that a long, kind of ugly expression like what we started with reduces all the way down to just cosecant squared. So that was fun. Let's try another. Okay. It looks like it's a pretty similar setup. We have secant plus 1 times secant minus 1 all over sine squared. Just like before, I'm going to start first by multiplying out the two factors in the numerator. And I notice again that it's going to be a nice difference of squares. And if difference of squares seems a little bit confusing, don't worry about it. You're A-okay foiling it out, distributing it out, you're good. So I'm going to take that first term and square it. Difference is another word for subtracting, and that's a good key of how we'd always have a negative sign separating the two squares. So that's my numerator, and sine x squared tags along in the denominator for the ride. Once again, I'm going to think about what is a identity that I can use. I mentioned before that anytime I have a trig function being squared, especially if it's being added or subtracted with 1, that's a big warning bell that I might be able to use a Pythagorean identity. And I've said that they are my absolute favorite. So I'm going to look and see if there's any Pythagorean identities that I can use with secant squared x minus 1. And I hope you guessed that yes, there is one. 1 plus tangent squared x equals secant squared x is one of the ways we write it. Just like before, I want to manipulate this equation into something that I can use and substitute into the expression that I'm working with. So I'm going to subtract 1 from both sides. Then I have tangent squared x equals secant squared x minus 1. I have a secant squared x over here, and I have a secant squared x over here. Secant squared x minus 1 always is going to equal secant squared x minus 1. So that's telling me that I can substitute tangent squared x for my numerator and keep sine squared x in my denominator. Just like before, I could stop here, but a part of simplifying identities is knowing how far to go. We want it to be the smallest unit possible. And I know that I can keep going here. So I say, all right, tangent, we know, is really sine over cosine, all over our denominator. That's sine squared x. So what I'm going to do from here, same thing as before. We remember our fraction division. My numerator, that's sine squared over cosine squared, stays the same. Now it's being multiplied by the reciprocal of the denominator. I have a sine squared x in the numerator and a sine squared x in the denominator. I know that these divide out to 1 because anything over itself divides out to 1. What am I left with? 1 over cosine squared x. And one more step, because we want it to be the cleanest possible. I look at my reciprocal identities and I say, okay, 1 over cosine squared x has got to be secant squared x. All right. So this is, to me, this is really fun. A lot of students struggle with it, and we'll work with it in class. It's a lot of playing around and saying, I think I could use a Pythagorean identity here. Let's try it. So let's keep going. Okay. So when we're simplifying, we're starting with a big, I call them ugly expressions that we want to whittle down until it's the most simple possible. We're only working with expressions. Expressions meaning a term that doesn't have an equal sign. Sometimes we'll be asked to solve. This is something that we're used to in math. Solve for x. Solve for the side. When we're solving trig equations, what we're looking for is something equals something else. In this case, I'm looking for the solutions in a specific interval that will make this statement true. So I'm looking for values of x or theta in radians that will make this statement true. So just like before, when we would solve equations, I know that it can be really helpful to have one side set equal to 0. So I'm going to subtract 1 from both sides. So I get 2 sine squared x plus sine x minus 1 equals 0. Now, I don't know about you, but that sounds like a lot of writing to me. And that's okay. I'm not afraid of writing. But if I can use a tool to make this a little bit easier for me while I'm doing some math, I'd like to do that. So in higher level math, we do something called a U substitution. All it is saying, we're going to take out this term for a moment, and we're going to set it to U. Right now, I'm going to do a P substitution, because P for pre-calc. And I'm going to say, okay, for a moment, I'm going to let P equal sine x. What that's going to do is it's not going to change the answer or anything. All I'm doing is saying, okay, for the moment, while I'm doing some calculations, maybe I'll just shorten it. Instead of writing sine x over and over, this is something that can help me and make it look a little bit more familiar. Now we have 2p squared plus p minus 1 equals 0. This is something that we would have done, I believe, in chapter 2 when we were doing quadratics and factoring. I said factoring never ever goes away. Here it is. Now, when I have it written in the sign form, it might have been a little bit more tricky to see how I can factor it. When I do something called a P substitution, it might make a little bit more sense to us. It looks more familiar, and that's great. So, can I factor it? Of course I can. If you need a review on factoring, I would recommend Khan Academy. Khan Academy is great, always. Okay. So when I factor my equation in green, I get quantity of 2p minus 1 times quantity p plus 1 equals 0. And just like before when we were solving for quadratics, I'm going to set each of these terms to 0. So I get that p is positive 1/2 and p is negative 1. Which is cool, but I wasn't solving for what p is. I want to know solutions of x in a specific interval, 0 to 2 pi, that's going to make this statement true. That's when we have to go back and reinsert our function into sine x. So here, if p equals 1/2, I can say sine x equals 1/2. And if over here, p equals negative 1, I can say sine of x equals negative 1. Okay. Because we want to make sure that we are solving for x, not p. Now we go back to our unit circle. Trig builds off of itself a lot. And if I am, here's what we're looking for is solutions of the interval 0 to 2 pi. That's a hint that we're looking for angles, specifically radians. And we know that x is an arbitrary value. It's It's our variable. It's what we're solving for. We don't know what it is, and we're looking for it. So it's our angle measurement. I want to know from the unit circle what values of x in radians make it so that sine of that radian equals 1/2. Specifically, a positive 1/2. I also want to know what values of x give me that sine x equals -1. I like to start with my 1s, 0s, -1s because I think that they're the easiest. I know that the only time on the unit circle from 0 to 2 pi when sine is -1 is at 3 pi over 2. 1/2 is a little bit trickier, but we know how to use our unit circle. I figure out that I have the values 5 pi over 6 and a positive pi over 6. These are all of my angle measurements, and that's what I was looking for. Because I know that if I insert any of these angle measurements into x for that equation, it's going to be true. And you can test it. It'd be fun. I hope it's not too scary so far. We are going to try another one. Okay, this one's a little bit different. I don't have any factoring, but I still have some stuff that I can do, which is pretty similar to the simplifying that we were doing earlier. Here I have cosine cubed x over sine x equals cotangent of x. We're still looking for solutions, meaning that we're solving. I'm going to have something equal something else as my answer. And in this case, I know that I'm looking for radian measures in the interval 0 to 2 pi that make this statement true. So I think a good step is anytime I have cotangent or tangent, I like to see if writing it out as its quotient form will help me out at all. So cosine cubed x over sine x equals, I know that cotangent is cosine over sine. I'm looking here, is there anything that I can do? I am personally thinking I have a sine x in both denominators and I don't have any other terms. If I multiply both sides by a sine x, I get rid of my denominators. They're gone. All I have to focus now is on cosine cubed x equals cosine x. Now, this is a tricky point because before we had sine x in the denominator. And when I get to this step, it might be really, really tempting to divide by cosine. Divide both sides by cosine, set my remainder to 0, but that's not the case. If you remember when we were doing rational functions, meaning functions that have x's in the denominator, we know that dividing things out can absolutely change the results. So as tempting as it is, we can't do that. Sine x was already in the denominator. It was part of the function. Cosine x, we can't put it in the denominator in this case. We can't divide by it because that's going to change our equation a lot. So I'm going to subtract by both sides. I'm going to subtract cosine x from both sides. So then I'm left with cosine cubed x minus cosine x equals 0. This is pretty similar to solving. If doing that substitution that I talked about earlier, where I choose my favorite letter, not x, and set that equal to cosine x, you can absolutely do that. But here I see it's not too different from what we did at the very beginning of this video when I said, okay, what is the greatest common factor in both terms? I can pretty easily see that it is cosine x. So I'm going to factor that out from both of my terms. And just like before, I can set both of those terms equal to 0. So cosine x equals equals 0, cosine squared x minus 1 equals 0. I know that I'm looking for values of x, radians, that make my statement true. So think about your unit circle. What values of x allow our cosine to equal 0? Give me a second. Cosine is 0 along the vertical axis. So our pi over 2 and our 3 pi over 2 values. Now let's look at the other equation I have. Cosine squared x minus 1 equals 0. Now, I mentioned before, whenever I see a cosine squared x or any other trig function squared, I might be tempted to use a Pythagorean identity, but I'm really close, and I know that I can pretty easily solve from here because we're solving and not simplifying. So first, I'm going to do what I would do any other time if I had an x squared minus 1. I'm going to add 1 to both sides. Now I have a cosine squared x equals 1, which is pretty close to what I want. I want it to be cosine equals something. I'm going to take the square root of both sides. See how all of this math that we've done before just keeps coming around and coming back. Math doesn't go away. It just keeps building up on itself. So when I take the square root of something, there's a little thing that we often forget, our plus or minus. And that's really important, especially when we're solving for solutions, because we don't know if our cosine is going to be a positive one or a negative one. We have to account for both. So I say, okay, what on my unit circle is the cosine equal to positive or negative 1? I know that that's along the x-axis at our values of 0, pi, and 2 pi. So if I add all of our solutions up, I have that x is going to equal 0, pi over 2. It's going to equal pi. It's going to equal 3 pi over 2 and 2 pi. X is all of these values. It hits every single point along the axes. Right. All right. Simplifying by combining fractions. We've been doing a lot of solving where I'm trying to get an x equals. Here I'm simplifying. I'm taking a pretty ugly expression and I'm trying to break it down until it's as small as I can get it. And combining fractions. What does that mean? Well, bringing together fractions, we have fractions. This is another reason why I asked you to brush up on your fraction rules. Sometimes we get tempted to just add them straight across, and we know that is not how fractions work. I know that if I'm adding fractions together, I need a common denominator. Back when we were in maybe 5th grade, we would have looked at each of the factors and tried to get the smallest common denominator, the least common denominator. Here with trig, there's not really much I can do with a cosine to break it down. So I say, okay, one of my denominators has a cosine, so that has to be in my common denominator. My other denominator has a 1 minus sine x, so that also has to be my common denominator, because they have to share everything. Now we're going to try and add them together, but I have to do a step first. I have to work with that common denominator. So my left side is missing a cosine x in its denominator. And our right side is missing a 1 minus sine x in its denominator. And if you'll notice, I'm doing something that we've done for a long time. If I want to change the denominator, I have to multiply by 1. I can't actually change my fraction, but I can change the way that it looks. So if I use a cosine over cosine, I know that anything over itself divides out to 1, and therefore I'm not really changing the function. I'm just changing how it looks. All right, let's do some multiplication. I'm going to multiply my cosine times my cosine in the numerators. I'm going to get cosine squared x over cosine x 1 minus sine x. You don't have to distribute it. In fact, when you're simplifying, it might be easiest to just leave everything as outside as it can be, especially in denominators, because we want to see if things will divide out. So that's my left side. I'm going to multiply my right side by 1 minus sine x over 1 minus sine x to get sine x minus sine squared x all over cosine x 1 minus sine x. All right, something that's super duper important is I have that negative sign. If I have that, that means I'm going to have to distribute a negative. So this is really going to be a negative sine x plus a sine x squared. And what is that going to do when I swoosh them together? Because now they have a common denominator, I can add them together. No problem. Cosine squared x plus sine squared x minus sine x over cosine x times 1 minus sine x. Still a lot. Now, remember how earlier I was saying that if there's ever a time that I have a trig function squared, I should be a little bit suspicious to see, can I use a Pythagorean identity? If I ever have a cosine squared x plus a sine squared x, that is the biggest warning bell that I'm probably, not always, going to use a Pythagorean identity, because I think that the number 1 is a little bit more simple than writing cosine squared x plus sine squared x. So I'm going to substitute it. That's going to turn my function into 1 minus sine x over cosine x times 1 minus 1 minus sine x. Awesome. What can I do from here? I see that I have a 1 minus sine x as a whole term in the numerator and in the denominator. I know anything over itself divides out to 1, and I can divide it out because it's in every piece of the numerator. There's only one numerator, right? What that leaves me with is 1 over cosine x, and I use my reciprocal identities to know that, okay, that's actually the secant of x. A lot of work to boil down 2 fractions down to secant of x. But what we're doing here is we're showing that we really do know how to manipulate and use our trig identities. And that's a lot of what analytic trig is about. All right, so what we're going to do when we get back is we're going to continue this a little bit. We're going to look at how can we solve graphically using our graphing calculators, and we're going to do a lot of practice examples. If you're using the guided notes, then you would see that I have 2 examples on the back with some of the steps blocked out. Go ahead and try those, and if you want to try the homework, go ahead. But otherwise, have an awesome 5-day weekend, and I will see you on Wednesday.